Good morning, Panthers. We come to a pet peeve of mine. This covers section 9.9 intro, exceptions to the octet rule. And we've talked about the octet rule as if this is like hard, fast rule, like it's like the speed of light or something, it can't be violated. And as you know in chemistry, there are always exceptions. So this is one of the things that makes chemistry interesting and one of the things that makes it fun. So today's topic is going to be exceptions to the octet rule. But here's the first thing I want you to remember. These exceptions are relatively rare, and you should not be looking for exceptions no matter where you go. Now, the reason why I call this a pet peeve is there are some faculty who seem to believe that by putting exceptions to the octet rule is fun on an exam. If I write an exam, I'll usually have 7 or 8 Lewis structure type things and maybe one exception, maybe 2 exceptions to the octet rule. I have seen cases of people who remain nameless who will have 10 Lewis structure type problems and 8 of them are exceptions to the octet rule. These are quite rare in nature. Things that violate the octet rule are not very common, and you're not very likely to encounter them. I haven't really encountered them very much in my career. So I'm not going to spend a ton of time on exceptions to the octet rule. I am going to tell you that they don't happen very often, so you shouldn't be looking for them all the time. But they do happen, so you do need to be aware that such things exist. So there are 3 different types of exceptions to the octet rule, called the incomplete octet, odd number of electrons, and expanded octet. These are written in order of increasing likelihood. Okay, the expanded octet happens much more frequently than the other 2, and the other 2 are for very specific cases. So let's start with the incomplete octet. That just means there's not enough electrons to go around to give you an octet. And this tends to happen with elements on the left side of the periodic table, like boron and beryllium and aluminum. Those are the 3 that typically this might happen to. So I'll give you an example of this. Beryllium dihydride. That's a real molecule. And the Lewis structure looks like this. Okay, hydrogen only has 1 valence electron, beryllium only has 2 valence electrons, and you end up with a Lewis structure where you only have 4 electrons around the central atom. There's no other way to write this. There's only 4 total electrons, so you have an incomplete octet. I've never seen beryllium dihydride. I don't know what beryllium dihydride does. It does exist, but it's not very common. Boron trifluoride, it would be another example. Aluminum trichloride would be another example. I have actually done an experiment that involved aluminum trichloride, so that one does exist. These are not very common again. Boron, central atom, fluorine are the outside atoms. Aluminum is going to be the central atom. Chlorine is going to be the outside atoms. Remember, electronegativity differences are going to make it such. Both boron and aluminum have 3 valence electrons, and both chlorine and fluorine have 7 times 3, so 21. So we need 24 total electrons. So you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Exact same structure here, except they're on chlorines. All right, incomplete octet. Neither aluminum nor boron have enough electrons. There's 24, we've already used them up. So the octet rule is not satisfied. For the boron, it only has 6 electrons around it. The aluminum only has 6 electrons around it. This beryllium only has 4 electrons around it. That's what the incomplete octet is. So if you're going to see an incomplete octet, look for elements like boron, beryllium, aluminum. It does not happen very often. It is not a common thing to occur in the lab. Like I said, I have seen aluminum trichloride. I've never even seen these other molecules before. All right, second case, odd number of electrons. You can convince yourself that if you have an odd number of electrons, you cannot make the octet rule work. It's impossible. So if it turns out when you add up all your valence electrons that you have an odd number of electrons, you are going to violate the octet rule. This does not happen very often either. The place, if you're going to see it anywhere, is nitrogen. Sometimes this happens with nitrogen. Now, just because you see a nitrogen does not mean it's going to violate the octet rule. I'm going to give you an example of one that does not violate the octet rule, something like ammonia. That's got a Lewis structure that looks like this. Okay, does not violate the octet rule. But there are compounds that do violate the octet rule. An example would be NO, also known as no. So that one has 5 valence electrons from the nitrogen, 6 from the oxygen. That's 11 valence electrons. All right, so if we write our skeletal structure, NO, 2, 4, 6, 8, 10, 11. And obviously the octet rule is not looking good here because we have an odd number of electrons. We have 7 electrons here and we have 6 electrons here. That does not look good. So we're going to move one of these lone pairs, as we've done several times before. Delete that. We still have 7 electrons around the nitrogen, but now we have 8 electrons. We have 8 electrons around the oxygen, but 7 electrons around the nitrogen. Now you might be asking yourself, well, how do you know to put this single electron around the nitrogen? You should put the single electron whichever one is coming with the odd number of electrons. Now remember, nitrogen only has 5 electrons, so that's probably where it's going to come from. Now, if you're not convinced of this and you're like, I don't know about that, I'm not sure about this, we'll check the formal charge just to see if it looks okay. So we'll take the oxygen case. You might remember we've done this one a few times, but if not, that's fine. The formal charge is equal to 6 minus 4 minus 1/2 times 4. That one's equal to 0. Okay, so the formal charge on that nitrogen is 0. The formal charge, or excuse me, on the oxygen, the nitrogen is a little bit of a weird one, 2 lone pairs and a single. So the formal charge on this is 5 minus 3 minus 1/2 times 4. So it's 5 minus 3 minus 2. Oh, that one's also equal to 0. All right, we've got zeros on both of these. That looks like a good Lewis structure for the odd number of electrons for the molecule NO, nitrogen monoxide, also known as NO. Okay, so that's second exception to the octet rule, odd number of electrons. You're not going to see it very often, but if you do, look for nitrogen where you are going to see it. All right, and the final exception to the octet rule is called the expanded octet. This one you will find more commonly, and the reason why is if you have an element in period 3 or below on the periodic table, there are d orbitals. So because there's d orbitals, we can put electrons into the seats of the d orbitals. So you're not going to find the expanded octet in period 1 or period 2. Hydrogen, helium, or any of the period 2 elements, you're not going to find an expanded octet. And by expanded octet, we mean more than 8 electrons around the central atom. But if you're in period 3 or below, it is possible. So a couple of examples of this would be something like SF6, PCl5, xenon, tetrachloride. So you notice all of these are in period 3 and below. And so SF6 looks something like this. You can count all the valence electrons and convince yourself this is correct. But it looks something like this structure right here. So sulfur hexafluoride looks like that structure. Obviously, the octet rule is violated for the sulfur in the middle. It's allowed to happen because of the d orbitals. PCl5 looks like this. Phosphorus pentachloride. And xenon. Okay, there are obviously other molecules that do this. These are not the only three, but I'm just giving an example of 3 different molecules that can violate the octet rule because of the expanded octet. I'm going to reiterate again. These molecules can, they're not necessarily going to. That should not be your go-to. Just because you, in other words, just because you see sulfur in a molecule should not mean that you're automatically going to look to violate the octet rule. It can be violated, but that should not be your go-to position. You should look for it keeping the octet rule, and if there's no way you can do it with the octet rule, then fine, go ahead and try a structure where you violate the octet rule. You can then use formal charges to check to see if it's correct. All right, that's our exceptions to the octet rule.